look at these answers. Now, I will tell you that this answer right here, I don't know, was okay a couple weeks ago, but it's not okay now. I expect everyone to give it a try, okay? To at least put something down and get as close to it as possible. So be aware that it may have been okay before, but not now. Okay, so I've got lots of, you can see what I look at when I look at your papers, and everyone has something. Some of them are equivalent and some of them are not. So let's do this. Let's go to our work. Let's look at what we come up with, and we'll kind of compare it against what some of these answers are, and then you'll know which one was yours and if it was close. So let's see. If I'm going to take the derivative of this, my outside function is something to the 1/2 power. So let me put this down, derivative with respect to x. We'll put our work in first. And then, okay. So before I do that, let's look at this. We might as well do some algebra along the way. If I have negative 1 x to the negative 2, how about negative 1 divided by x squared? Might as well put that in now. Plus, okay, so now I've got 1/2 cosine x to the negative 1/2, that's the outside, times the derivative with respect to x of cosine x. So my derivative is negative 1 divided by x squared, plus, now as I go through this I can do some algebra also. If I have cosine x to the negative 1/2, 1 divided by square root of cosine x, times, what's the cosine, derivative of cosine? Yeah, it's negative sine x. So we could end up with the derivative of y with respect to x as negative 1 divided by x squared minus sine x divided by 2 square root cosine x. So let's see. How many people can we pick up that had an answer that was fairly or close or is correct? I think we forgot. Well, I was only asking you for this part, wasn't I? That's right. Okay, so we don't need to look at all of it. I would say that one's correct. This one is correct, but it doesn't have the positive exponents. So I would say correct on here. I think the same thing for this one. So I would think these two are the same, aren't they?
What do you mean it doesn't have positive exponents?
Well, isn't this a negative 1/2?
There's a negative one.
Yeah. It's in this.
You can't, it's not this equals.
Okay, so I'm looking at the fact that this, are we disagreeing that this has a negative 1/2 here?
No, the one.
It is there.
Yeah, I don't want any negative exponents. Okay, so if they are negative, we want to make them positive. Okay, so these are correct. I think these three are correct, except that we don't have positive exponents only. Same thing for this one. This person used decimal, which is okay, but still it represents a negative exponent, so we want that. If you didn't have the correct answer, make sure you go back and look at this problem again. This person, this is good, okay? But some of you, I think, forgot the fact that we have the outside function. And when we talk about the outside function, you know, it's like having those, you know, covering it up with something, whether you want smiley faces or stars or whatever. Let's get back to our work here. So what if I have something to the 1/2, what's the derivative of that? 1/2 the something to the negative 1/2. I have to have that. Scott, you had a question?
If there's a square root in the denominator, would you rather have it as x raised to the 1/2
Yeah, I'm happy. I'm happy like that. Okay, that's not a problem. That's not a problem. Okay, we want to check our answer again, of course, against the Inspire to make sure that it was correct. Okay, let's continue on. We've got a lot more we need to talk about here. Okay, let's go on to the next problem. I'm not going to work all of these out completely because after a while what we're doing is just repetitive work. Yeah, Heather?
The last problem is just the excellent point.
Oh, forgot that, didn't I? At a certain point, absolutely. Thank you. We wouldn't be complete without that. Okay, so at the input of what, Heather? Pi divided by 2. So I'd have negative 1 divided by pi divided by 2 squared minus the sine of pi divided by 2 divided by 2 times the square root of the cosine of pi divided by 2. So now we got to figure out what exactly is the cosine and sine of pi divided by 2. I'm going to go back to my circle here, unit circle. Pi divided by 2 is radians is equivalent to how many degrees? 90 degrees, which makes the terminal side right up here. That terminal side has coordinates of 0, 1, which means the cosine of pi divided by 2 is 0. Red flag goes up. What do you know about this fraction? It's undefined. Now, just because this fraction is undefined, does that affect this one? That still has a value. But what is it? How does it affect the whole? Makes it all undefined. Okay, so it's all undefined. So there is no derivative. Now, what does that mean for us? Well, it could mean that there is no tangent at that point. We'd have to go back into this function and look at it. Is it one of those where we have, it's like something like this happening, where we end up with a vertical line? Is it something where we have a sharp point, and that's why it doesn't happen? Is it by chance, like, cosine in the denominator is secant, and so we know that has a series of these happening. Is it because we have a vertical asymptote? We'd have to go in and look at that and find out. Jordan?
So if it is undefined, do you want us to do like what we did for the limits and provide a reason?
What I would probably do for this one is say, show me graphically. Okay, and then you can, you'll discover one way or the other on that one. Okay, thanks, Heather, for bringing us back to that. Again, because of time, I don't want to take all of these to completion. This is finding the equation of a tangent, but I do want to talk about this because we're in section 3.4. You tell me, is there a composite function here? Allie says yes. Is it Allie? Yes. Okay, Allie says yes. So if we're looking at that and we take a look at our derivative, one of the questions is what happens with that 2 out in front? Well, if I take that factor, that 2 as a factor, we would then use the product rule on this. And as the product rule, I'd have the first factor times the derivative of the second, which is where I need the chain rule, plus the second factor times the derivative of the first. Well, what's the derivative of 2? 0. So the second part of the product rule is just going to be 0. You can either go through and use the product rule on this, or you can say, hey, that's a scalar. And as a scalar, I just bring it down. Okay? Why? Because the product rule starts with the first factor and then the derivative of the second one. And that's where that brings it down as just a scalar. So if we're going to use, take the derivative of this, what we might want to do, what's another way of writing tangent cubed x? Yeah, I could write that as, I think I heard you say this, tangent x quantity cubed. Okay, so, if this is my function, and it's the composite here, then I've got 3 times the something squared, so I have 3 times tangent x squared, and then the derivative with respect to x of tangent x. So this would be the chain rule that we would be using. Now, what's the derivative of tangent? Go back and look. It's not one of those that comes up all the time. You could actually make it a quotient by sine divided by cosine and come up with it, but you can. I also will just let you go back and look at that if I happen to put one on, because again, it's not one that we use all the time. In order for you to check your answers, let me just go down to the final answer for this, and again, we're looking for the equation of the tangent, and you can check your work against this as another practice problem. Can't read my own writing there. I think that's a, yeah. Okay, so that would be the equation there. And again, it just would make it a nice little second, an additional practice problem. But it's taking the derivative first, and again, identifying is it a composite function. Once you've got that, what's your inside function, what's your outside function, and then knowing that you take a chain of those. Danielle? Okay, it's almost, thank you, I was looking at that too. Okay, part of what's in this section is not only the composite rule, but also a look at some of the rules that involve our logarithmetic and exponential functions. Within these, we use the chain rule in order to use them. So this is that derivative I gave you on the very first one. The derivative of the natural log function is 1 divided by x. What is x? X is the quantity in here. And I'm going to change this to d du of the natural log of u. In other words, if I have something other than just simple x, this is where the chain rule comes in. My inside function is u, and so that's the, let me put this in my blue color here. This piece right here is the inside function, and the inside function would be the value, that's a u here, natural log of u. Where's 1 divided by u? Well, if I take the natural log of something, it's 1 divided by that something. And then this is the derivative of the inside. Okay, we're going to have lots of practice on these. Let's start with this one. Do we see a composite function? We always start with that. And again, ask yourself this question. Okay, what if I was given x is equal to 7? Where would I start? And I would start in here. Okay, I would take 7 cubed. Then I would take the natural log. Okay, so that's how we can always help ourselves out with this. The other thing is that sometimes, you know, if I'm looking at the, let me go back here just for a moment. There was a problem back here that, here we go, back to this problem. What's the graph of negative 3x? Just a straight line, right? Downhill? Okay. What's the graph of e to a power? Yeah, it's an exponential curve in some way. Okay. If you're going to look at the graph of this function, would you expect it to look like a straight line or like an exponential? Exponential, yeah. Okay.